Welcome to the deep dive. Today we're looking at something surprisingly elegant that's hidden inside the biggest AI models you're using every day.
We're talking about models like Llama, Mistral, Prima, all the big ones.
And the challenge they all have to solve is, on the surface, pretty simple. How does a model remember the order of words?
It sounds basic, but it's everything. It's the difference between the cat sat on the mat and, the mat sat on the cat.
Exactly. Sequence is meaning.
And historically, this is a huge computational problem. Models would either have to use these absolute position number, like stamping position 1, position 2, on everything.
Which gets really messy with long sequences, like what happens at word 8,000.
It just doesn't scale well, so
Yeah.
they found a shortcut, a geometric one.
And that's our mission for this deep dive. We are going to unpack the specific, highly efficient code. It's just 3 PyTorch functions that handles all the sequence memory.
We're talking about rotary positional embedding, or RoPE.
We want to show you the mathematical trick that gives these models their speed and their sense of order.
Yeah, we're going to trace the whole process, from setting up the rules of rotation all the way to the moment that memory gets injected into the word vectors.
And you'll see that the secret to how AI handles sequence is all about, believe it or not, simple geometry and complex numbers.
It's a beautiful piece of engineering.
Okay, let's get into it. The conceptual core of RoPE. If we're not using absolute numbers, position 1, 2, 3, how on earth does the model know that cat came right before sat?
Well, RoPE works by subtly altering the internal representation of every single word.
Okay.
Think of every word deep inside the model as an arrow, a vector with, say, thousands of numbers just floating in this high-dimensional space.
A vector, right.
RoPE just rotates that arrow.
So if I have a sentence, the word at position 10 gets rotated a little bit.
A little bit, yeah.
And the word at position 100 gets rotated a lot more. The position itself dictates the angle of rotation.
Exactly.
Mm-hmm.
But here's the really critical insight, and this is why RoPE is so clever. The model doesn't actually care about the absolute angle of that arrow.
It doesn't.
No. It's only interested in the difference between the rotation of word A and the rotation of word B.
So when the model is comparing cat, which might be rotated 5 degrees, to sat, which is rotated 6 degrees.
That 1 degree difference tells the system everything.
It tells they're right next to each other, and the direction of that difference says which one came first.
Precisely. It's inherently relative positional encoding. You don't need to know where you are in the whole sentence. You just need to know your relationship to your neighbors.
And that's why it scales so well. The relationship between words at position 100 and 105 is the same as the relationship between words at, 7,000 and 7,005?
It makes the whole system incredibly robust.
And this rotation, it's applied specifically to the query and key vectors inside the attention mechanism, right? Just before the model figures out how words influence each other.
That's right. And you see this in modern architectures like Lemma. They use these optimized systems, something called grouped query attention, or GQA.
Right, where you might have, say, 32 query heads, but only 8 key heads.
Yeah, and you might think that complicates things.
It does it.
Not for RoPE, because the rotation is just an element-wise operation. It works on the underlying vector itself. It scales perfectly, doesn't matter how many heads are grouped together.
It's a universal trick.
It really is. It just applies consistently across every single one of those 128 dimensions in each head.
Okay, so if we're all in on geometry being the answer, that brings us to the engineering problem. You can't be calculating these angles on the fly for thousands of words every single step.
No way. It would completely crush performance.
You'd grind to a halt.
You would. So you have to pre-calculate every rotation instruction the model might ever need. And that brings us to the first function in the code.
The setup phase. This is pre-compute Frexis. And the goal here is to create a big lookup table of all the rotation instructions.
Right, a table we call Frexis. And if you just look at the inputs for this function, they tell the whole story.
Okay, so you need dim. That's how wide the word vector is, maybe 4096 numbers.
Yep, and you need end, which is the longest sequence it can handle, say 892 tokens.
But then you get this third input, theta, and it's set to this kind of magic number, 10,000.
A famous 10,000.
It seems so arbitrary. Why 10,000? Why not 1,000 or 100,000?
Well, this is one of the most fundamental design choices in RoPE. The theta value, it basically controls the maximum wavelength of the rotation.
For wavelength, so how slowly it can possibly rotate.
Exactly. If you set it too small, the rotation happens too fast, and you lose the ability to track relationships between words that are really far apart.
So setting it to 10,000 ensures the model can still tell the relative positions of words that are maybe thousands of tokens apart.
It's a scaling knob. It defines the ceiling of what the model can remember spatially.
Okay, so what's fascinating to me is how the code uses these inputs. It doesn't just assign one rotation speed to the whole 409d6 dimensional vector.
No, it's much smarter than that. This is the real insight into how RoPE handles locality. It takes the vector dimensions and works in pairs.
Right.
For the first few pairs, the low-index features, it assigns rotation speeds that are relatively fast.
Meaning those parts of the vector are really sensitive to small changes in position. They rotate a lot, even if the words are only a few tokens apart.
Precisely. Those high-frequency, fast-rotating parts are fantastic at capturing local relationships, grammar, syntax, immediate neighbors.
But then as you move down the vector to the higher index features,
The code uses that theta constant to calculate speeds that are dramatically slower.
and the slow rotation is for the global context, the big picture.
Absolutely. The high-index, slow-rotating features, they barely change their orientation over hundreds of tokens.
So the model can still connect a topic sentence at the beginning with a conclusion 500 tokens later.
Because those parts of the vector are rotating slowly enough not to get blurred out by all the noise in between.
It's like having two different kinds of memory cells, one for the super local grammar and one for the global story.
That's a great way to put it. And the formula, it uses torch.outer to calculate the exact angle for every dimension at every single position.
Giving you this giant table of angles.
But here comes the computational masterstroke, the complex number trick.
This is the cool part.
The final step in this pre-computation is using a function, torch.polar, to turn every single one of those angles into a complex number on the unit circle.
So that final table, Frex's, it's not full of angles anymore. It's full of numbers in the form of cosine theta plus I sine theta.
Yes.
Why do that? Why do all that conversion? Why not just store the cosines and sines and do the math later?
Because multiplying by a complex number on the unit circle is the ultimate computational shortcut for pure rotation.
A shortcut.
It lets us bypass the need to manually compute the classic rotation formula, which is, 4 separate multiplications and additions for every pair of numbers.
Oh, wow.
By packaging the cosine and sine into one single complex number now, we set ourselves up for a blazing fast computation in the next step.
So we've got this massive lookup table of rotation instructions, all packaged up as complex numbers, ready to go.
Ready to go.
Which brings us to the application phase. We need to rotate the actual data. The query vectors, xq, and the key vectors, xk.
We do. But first, there's a tiny but critical housekeeping step. The second function in our pipeline, we have to make the instruction table fit the data.
Right. Function 2, reshape for broadcast. This sounds a bit boring, but it's pure optimization, isn't it?
It really is. The problem is our query and key data is huge. It's often a 4-dimensional tensor. Batch size, number of heads, sequence length, and head dimension.
But our rotation table is just 2 dimensions, sequence length and head dimension.
And if you try to multiply those, the software will just yell at you. The shapes don't match.
So this tiny function just adds a couple of ones into the shape of the rotation table.
Exactly, in the batch and head dimensions.
And why is that so important? Why not just make the rotation table the full 4D size to begin with?
Because that rotation table is the exact same for every single batch and for every single attention head in the model.
So you don't want to waste memory and time copying it over and over.
You'd kill performance. By adding those ones, you let PyTorch's internal systems use something called broadcasting. It just efficiently sort of stretches or copies that rotation instruction across all 32 heads in every batch all at once.
Without the computational cost of actually creating that giant tensor.
A huge optimization for speed.
Okay, so the shapes are fixed, the instructions are broadcasted, and we're ready for the final step.
Yeah.
This is where the magic really happens. Function 3, apply roterium.
This function is beautiful. It's so short, but it does so much. It starts by taking the query vector, a sequence of numbers like A, B, C, D, E, F, G, H.
And it reinterprets them. It looks at them in pairs.
Yes. It essentially tells the model to view the vector through the lens of complex numbers. The pair, A, B, is now treated as a plus by.
And that's just a single operator call, torch.view as complex. So simple.
By doing that, we've now turned 2 real numbers into one complex number.
Yeah.
And now we're ready for the payoff from all that pre-computation.
This is where the efficiency gain just hits maximum velocity. The very next line of code is just a simple multiplication.
The complex query vector multiplied by the broadcasted complex rotation table.
And that one multiplication is the shortcut.
That's the entire shortcut. If we had tried to do this manually with real numbers, we would have had to write out the full classic RoPE formula.
The A times cosine theta minus B times sine theta?
Right, and a times sine theta plus B times cosine theta. It's messy.
That's 4 arithmetic operations for every single pair of numbers.
Exactly. But thanks to the rules of complex number arithmetic, that single multiplication operation automatically calculates all 4 of those operations at once.
And the output is the new rotated position.
All executed incredibly quickly by highly optimized hardware instructions.
So you trade 4 explicit trigonometric terms for 1 simple multiplication sign. That is pure engineering genius right there.
It really is. The output is still a complex number, of course, representing the rotated vector. So the final step is just converting it back into real floating point numbers.
Ready for the attention mechanism to use.
And that's it.
So if we pull this all together, the whole pipeline is just these 3 unified, super optimized steps.
Right. First, you pre-compute all your relative positional instructions, and you package them as complex numbers.
Then you reshape those instructions so they can be efficiently broadcast, distributed to all the data at once.
And then you apply the geometric rotation almost instantly using a single complex number multiplication on the query in key vectors.
And that holistic approach, that is the so what factor, isn't it? This exact implementation is copied everywhere.
Llama, Mistral, Gemma, they all use it because it's simple, it's mathematically elegant, and most importantly, it is incredibly fast.
Which you absolutely need when you're pushing context windows up to 8,000 tokens, 16,000 tokens, or even more.
You need every single optimization you can get.
And the model gets this robust sequence memory without any of the headaches of absolute positioning. It just relies on the relative angle between any 2 words.
Which lets it generalize to longer sequences so effortlessly. The whole architecture is just stable and predictable.
The simplicity is really the key. The rotation is always relative.
The size of the angular difference tells you the distance, and the different rotation speeds, fast for local, slow for global, make sure that both short-term grammar and long-term narrative are encoded at the same time.
So this whole deep dive, it really shows that the complex math of RoPE, it lets these AI models remember order, not by stamping positions on things,
No, not at all.
but by constantly adjusting the orientation of a word's meaning. It's like having hundreds of precisely calibrated spinning clock hands.
That's a perfect analogy. Some are capturing those tiny local ticks, and others are capturing the huge, sweeping changes of the entire story.
It's an incredible solution, taking thousands of floating point numbers that describe a word
And turning them into a simple geometric rotation to show its exact place in a narrative. The engineering challenge that this solves is it's really something to appreciate.
It really is. And it makes you wonder, what other complex calculations in AI are secretly relying on these incredibly elegant, centuries-old mathematical shortcuts?
Hiding behind efficient operators like complex number arithmetic, just waiting for us to uncover that level of elegant implementation.
That, perhaps, is the next frontier of AI efficiency.
I think it might be.
Something to mull over until our next deep dive.